it's like a Zoom call in the same way. Yeah, so sometimes in life, you meet somebody who deeply inspires you. So Qiang is not only a really creative researcher and an influential writer, he's also a great mentor for early career mathematicians. So many of us profoundly admire him. He's currently the Fu Foundation Professor of Applied Mathematics at the Department of Applied Physics and Applied Mathematics at Columbia University. He's made numerous research contributions in computational mathematics that have influenced material sciences, algebraic geometry, and biology, just to name a few. Of course, with that, he has many research awards. His latest one is the Hughes Medal, which is recognizing his creative contributions in computational physics and fluid dynamics. I guess we can add to this list of prestigious prizes because he's the first non-local, in-person Qiang colloquium speaker of the semester. So congratulations. He's also the author of a science book called Nonlocal Modeling, Analysis and Computations, as well as a co-author of an active numerical survey, Numerical Methods for Non-Local and Fractional Models. So today I'm very excited to hear about top science to consider non-local modeling from the world's expert on non-local modeling. So, take it away.
Thank you so much, Alex, for the generous introduction, and also thank you and thankfully to Cornell for inviting me down here. I have now traveled for the past 18 months, so this is my first trip out of Manhattan. Most of the time, my wife and I just stuck in our little apartment. So I really enjoyed the trip, an opportunity to come out, and of course, Cornell. I was talking to Alex. Cornell is actually one of the places I always wanted to visit, ever from my years as a graduate student more than 30 years ago. But I never made it here, and this is my first time. And the weather is beautiful, so
it's always that way.
So it's really, I have a lot of good friends, girlfriends, and also I met a number of new ones. It's been a very pleasant journey so far. I really enjoy the opportunity. Thank you. So today I'm going to talk a little bit about nonlocal modeling. This is an interest of mine for the last, I think, about 10 years or so. That shows how we haven't met each other for a while. All right. So I understand this is a colloquium lecture, so I'll try to make my lecture more general. And maybe towards the end, I'll try to say something more technical, but most of the time, I'll try to focus on the non-technical side. This lecture will talk about some common issues related to nonlocal modeling, analysis and computation, which happens to be the title of my book. I will start by talking about nonlocal model and to say what are they different from other models that maybe you're familiar with. And I'd like to spend more time talking about when to consider nonlocal modeling if you're interested in solving practical problems. Then I'll try to list a few things that we think is still challenging in nonlocal modeling. Hopefully, I will deliver a message to say that nonlocal model actually has a very long and a long history, and they're generic, they're very universal in nature, and they could be a good alternative to some more traditional local models. And also, at the same time, they can serve as bridges between different models and also inspire new mathematical tools. So after all, I am an applied mathematician. All right, so let's try to define what's called a nonlocal model. Now, things are all relative. We begin maybe to understand what's the meaning of local, right? So local often is interpreted as something confined at a particular point and maybe at a particular time, right? Then anything other than that, we can view this as non-local. So that's pretty general. You can try to give a more mathematical characterization. So we'll start with linear operators. So we want to study nonlinear ones, but let's begin with a linear operator. How do we differentiate, how do we distinguish local and non-local linear operators, right? So one definition can be done as follows. You think about operators acting on functions, in this case, just like finite dimensional functions, or functions defined in finite dimensional Euclidean space, functions to functions. A linear operator is called local, right? If the support of the image, so after you map the function to, that support is a subset of the support of the original function. Right? So it means that it cannot generate something from nothing. And if it's completely zero, then you're not going to get anything other than zero. Right? So this can be said as a non-increasing support. If you don't have that, then you can call this operator as a non-local. This is one definite, at least reasonably mathematically. Right? Now, there are many well-known examples of local operators. If you take derivatives, those typically are local operators, right? Because if you have a function that's going to be identical to zero on a range of part of the interval, if you differentiate, always end up with zero, right? So you're going to generate anything non-trivial. But the question is, are there other operators which are also local, besides the differential operators? So it turns out there is a theorem, so I'll call Peter's or Petri's theorem. It's a theorem proved quite a number of years ago. It says, in fact, local operators are pretty much like derivatives, right? So linear operators, which are local, are confined to polynomials of differentiation or derivative operators. Okay. So in some sense, the way to understand local operators and local models is to say, well, they're described by differential equations, where differential equations generically are local, but otherwise we'll have non-local models. Well, I mean, PDEs are tremendously popular. We've been using this all the time. So I know I'm coming to Cornell. This is actually I think in the forward preface of Steve's book, the popular book, Newton Powers. It says it's a really mysterious and marvelous fact that the law of nature always turned out to be differential equations. Right? So there are definitely truths to this. But today I also wanted to advocate maybe the other side of the story, that perhaps one can also step out of the box and think about something beyond the differential equations. Okay, let's follow this line of thinking a little bit further. If we recall, the theorem in function analysis, talk about how to represent linear operators. Generically, you can think about all linear operators as integral operators with a kernel representation. Right? So whether it's local or not, then just based on what kind of kernel you pick. And if we use the Peter's description, basically just says you're going to end up with local operator if this kernel K will be has supported on the diagonal in x equal to y, and also taking the form of finite combination of delta measures, right? So that's very limited. But then the non-local operators will be all the other kind of local operator kernels you can think of, right? They're going to make up non-local operators, and there are many very well-known examples that you may or may not think in this way. Certainly, Fourier transform is a linear transform, linear operator. If you put that one in by this definition, it's non-local, and we understand that, right? And so are many others, like convolution operators, or even if you're doing numerical analysis work, finite difference operators, right, with a finite mesh size h. If you're doing a shift operator, doing a difference operator, they can all be viewed as non-local operators because the kernel support does not lie on the diagonal of x equal to y. Okay. And then there are, graph Laplacians. People use non-local means in image analysis or diffusion maps, Colloquium and others for data analysis. So there are many popular non-local operators. Okay. And in fact, you can say non-local operators have a very long history. Maybe could be say as long as the local one or even longer. So in physics, non-local interactions also have been discussed quite a bit with the work of Lord Rayleigh, Van der Waals, Korteweg, and later on by Thomas Fermi and Landau. One of the things we see more often, for example, in quantum mechanics, we see more PDE description, is the fact that originally there could be a non-local interaction could play a very important role, but in those days, in older days, it's not easy to deal with them either analytically or computationally. There's no powerful computers to treat them. So for convenience, for other reasons, if you think about the quantity of interest is smooth in space and very slowly in space, that's a common assumption, then you can basically try to localize or approximate the non-local interactions using some local forms. People call this as non-local expansion. It's just basically like doing a Taylor expansion for the non-local operators. You truncate a certain order of derivatives, and you end up with a more standard differential form. Yeah, and you can see this kind of derivations a lot in Landau-Lipschitz and so forth. And of course, there are many more notable examples, say in mathematics or in physics or mechanics, in homogenization theory of heterogeneous material. Right? So generically, you're going to get, if you talk about homogenized limit, they could take a non-local form. And the cases we end up with PDEs are really very special with all the additional assumptions. If you try to derive sort of quantitative modeling of polymeric fluids, or maybe we discussed a little bit with Alex this morning, and there are also a lot of times that non-local models play very important roles. Although you don't see non-locality appears not often, because it was thought that anytime you see non-local things, you try to localize them. So you end up seeing more differential forms. Okay. Now I'm going to give you, so the examples I talked about before were more, things you've seen while we were in one place or another. But here are some new non-local operators that I've introduced, which played a very important role in some of the work we've been doing in the last 10 years or so. I'm going to define what's called a non-local gradient operator or divergence operators as some integral operators, right? But they're acting on vector fields because we're interested in describing problems from mechanics. And the quantity of interest is not necessarily a scalar equation, a scalar quantity, but rather a vector field or tensor field. So in that case, you need to take this more general form. They all appear as integral operators, except the kernels might look complicated, right? And the non-local divergence and non-local gradient, they will form in a natural sense a duality pair as what we see in the local case. And you can think about this duality as really a non-local integrated parts, or maybe just as a version of Fubini theorem. You can interchange of order of differentiations. So they do have meaningful correspondence with each other. If the operator you saw them the first time, integral operator, you don't have a very good intuition, then you can look at a particular special case, right? The case where you work with a scalar function, right? And then you can avoid some of the tensorial notations. Then a non-local derivative, right, for scalar function, you can just think about that as a weighted average of a difference operator. Right? So you take a first order finite difference, that weighs a particular scale S, and now you say I'm going to weight this with a particular weight function omega delta S, and then I'm going to integrate this over or average over a finite range going from 0 to delta. Right? So this is a non-local operator. This will form a non-local derivative in the sense that if you have a smooth quantity of interest, so if U is a differentiable, for example, right? And you can imagine that as delta is getting smaller and smaller, and if your kernel, your weight function, omega delta is also more and more concentrated, okay, in a good way, then the operator actually approximates the standard derivative operator. So there's certain consistency with the classical definition. And then what we have there for the vector fields are just generalizations of this very basic ones.
So I understand the role of delta there being the range of interactions, but what's the role of epsilon? You say for all epsilon.
Okay, sorry, yeah. So the delta quantifies, as Alex pointed out, delta quantifies this range of non-local interactions. I'm only going to be interested in interactions within a delta neighborhood at a particular point. Right? But this assumption of omega delta with this epsilon is really to say, if I put a cutoff for any interval, right, of any range of interactions, if I make delta smaller, my range of interaction will be within that one. So whatever is outside, eventually is going to go to 0. So they're less important. So that's the condition of omega delta to say, when delta gets smaller, I'm going to be more and more concentrated near the origin. Okay, so that will give you the localization effect. This is a technical assumption generally. Now, of course, you saw the non-local derivative, but you can go on to talk about some other non-local operators. So one thing that we use quite often is called non-local diffusion operator. Okay? And the way to think about that is you can cook up a standard center difference operator And then you say, well, let's take an integral average of that. I'm not going to take finite difference over a particular length scale. I'm going to average over a range of 0 to delta. This will give you let's see. So this will define an operator called L delta U, and that's called the nonlocal diffusion operator. Now, this nonlocal diffusion operator can also be written as a composition of a nonlocal gradient and nonlocal divergence in a way. Right? So just like the local one can be written that way. So you'll be introducing a pair of new operators. Well, we have G and G star. So one of them is just a divided difference. The other one is more average. And notice that they actually work on functions of defined on different domains. Right? So G itself acting on a function of a single variable, but it gives a meaning for any particular pair of points x and y. On the other hand, G star will map a function of two variables x and y and compress that back to a single variable. And the composition of the two will map a function of single variable back to a function of single variable. So that's what nonlocal diffusion does. Okay. Again, you can look at the local limit as a range of nonlocal interaction strings. Right? And these for smooth functions, this operator will approach to a second order derivative operator. Right? And you can look at examples where this may happen. One of those assumptions I made on the last transparency applies over here as well. Okay? At the same time, you can also look at other special cases. If you put your weight function, say for example, to be concentrated at a particular grid size, that's almost like a delta function. In this case, of course, your integral operator becomes the finite difference operator. So the nonlocal operators can take a local derivative as the limit, but it can also bridges with your finite difference operator, right, which is a discrete operator. Or you can spread your nonlocal kernel as a power function, and you can make your range of interaction go to infinity. In that case, you actually get a fractional operator, fractional diffusion operator, as some fractional power of your standard derivatives. So it means to say that we can have a nonlocal operator, pretty generic, and they can be related to differential operator, they can be related to difference operator, and they can also cover differential operator. So they are much more universal than what I can think of. I mentioned earlier the long history of nonlocal operators, right? So fractional operator turns out to be one that sort of studied in mathematics for ages. Back in the days when calculus was invented, there was a famous exchange between Rothko and Leibniz. So Rothko asked Leibniz, can we basically use half-order derivatives? And Leibniz at that time says, well, that's an interesting question. We don't know, but maybe one day there could be consequences, useful consequences to be drawn. And indeed, nowadays there are a lot of works about fractional derivatives and fractional operators. All right. So I've introduced quite a number of operators from nonlocal gradient to nonlocal divergence and all different kinds. I want to say that this is our effort to make them as some kind of building block of a nonlocal vector calculus to serve as a foundation to try to classify or try to analyze this nonlocal models. Because as we know, the local PDE's model is based on essentially the classical calculus. So how about nonlocal model, right? So we're trying to do that. And I'll show you this example in this context of Hydrodynamics. I was mentioning with Tim just a minute ago. This is a model of mechanics pioneered or invented by Stuart Schilling and Sandia National Lab. And this is done nearly 20 years ago. I'm going to pick up a very special case. It's actually going to be on a linear paradigm operator, right? So you can view this as an analog of linear elasticity model. Right? So we call this as a nonlocal bound-based paradigm model. It utilizes the force balance, but the force here is a nonlocal bound force written as an integral average, right, of pairwise bound force interactions. Right? If you're given a displacement field U and you want to compute the bound force, so what you do is you look at the relative displacement at any given pair of points within certain interaction neighborhood, and you average them all together. That's essentially sort of like the total bound force acting on a particular particle in a particular position. Okay. Now, if you give this to a mathematician or give it to this equal form, give it to someone who hasn't seen this before, it might look complicated, and you don't see what kind of structure you can have, or maybe it's hard to see how this is going to be related to, for example, linear elasticity, as we used to see from our mechanics course. Right? So let me just show you. If you introduce this nonlocal divergence nonlocal gradient operator as I did before, then this operator can be naturally written as a composition of the two basic operators. So you can draw the following comparison, right? So on one side, you can say how the Newton's vector calculus is made up, and how that's going to help you to write down the local PD model or study the local PD model. Then you can use this new set of building blocks, this new set of nonlocal operators to rewrite, for example, the nonlocal bound-based paradigms, right? So essentially, we like to have similar basic building blocks and similar mathematical principles. How to formulate nonlocal balance laws, and how do you do this kind of integral identities, like what's the first Green's identity in a nonlocal sense, right? So we can have analog in a nonlocal sense of what you know in the classical literature, okay? And then you can assign meanings to what would be a well-posed nonlocal equation, right? So in the local PD, you have the equation boundary condition, then you can talk about, in this context, the nonlocal equation and maybe nonlocal boundary condition, or nonlocal constraints, that's what we call it. All right, but I should make a comment to say that our effort is not try to duplicate what we know about PD or about classical calculus and just try to rewrite them, reinvent them for nonlocal models, right? But rather, we hope that this new set of thinking for nonlocal model, in fact, can offer some deeper insight not only into this nonlocal world, but also even give you a new perspective about a traditional local PDEs. Okay, so maybe you always think about local PDEs in a nonlocal way, but hopefully having a nonlocal generalization can help you understand the local model itself. And that's what maybe I'll try to say more in my lecture.
Are you going to say something about those non-local boundary conditions?
I may not be able to get into the specific, but I'm happy to talk to you more after the lecture. But there will be some aspect of that mentioned over here. Right? Okay, so let me first of all let me step back for a second. Right? I add one slide of comments. I will say maybe in some sense, nonlocal model is also pretty timely for people, for us to study, because we're living in a world that's different from the days of Newton or Leibniz, maybe in many ways. But certainly to me, I feel like we're in a much more connected world. The nonlocal effect seems to be stronger than ever, right? And so at the same time, we've all been using supercomputers or machine learning and so on, and they provided a different way of treating complexity than the days when Newton and Leibniz they basically just need pen and paper, doing things on with that. And maybe if you want to compute complicated integrals or derivatives, you just basically have to do Taylor expansion and work with polynomial approximation to that. But we're simply in a different world. So we should be able to handle more complicated information, more complicated models, and then we're seeing maybe stronger nonlocal effect. So all of that connected together says, well, maybe it is time to study nonlocal models. After all, the early part of my lecture trying to sell the idea they're more general, they connect many different operators together. Now, if we're lucky, we can have a good mathematical theory behind this, and also effective algorithms, and hopefully we can make a nonlocal model a very useful tool. Right? Okay, but then this goes back to the question: is if you want to try to study nonlocal models, when should we start thinking about it? So I give you some of the signs that I think maybe if you see some of them, maybe you should think about perhaps nonlocal modeling could be a possible perspective. Okay. All right, so I go through some of them one by one. Okay. The first one I would say Actually, non-locality is very generic. If you're doing multi-scale modeling, and if you want to do model reduction, reduce order modeling, or dimension reduction, I would say in that process, non-locality is fairly generic, right? There's some very simple examples, like if you have a PDE in a three-dimensional domain, but you want just to write this as an equation on a boundary, you can have a boundary integral formulation using Green's function, but that will become an integral equation. We all learned that from our PDE course. And if you're if you're an integer person, you can think about having a sparse matrix, but I want to solve that, obtaining the true complement, which could get into a dense matrix. That's non-locality. And certainly there are many other examples. So non-locality really is a generic feature whenever you want to do dimension reduction, but you want to account for some of the unresolved scales. You don't want to just throw them completely away in this multi-scale setting. There's some maybe more well-known ones. Maurice-Wansek, this is mechanics. This is one way to say, you're going to, if you want to account for the lower dimensional, the higher dimensional effects, maybe view them as some kind of noise or simple fluctuations, then it's going to bring in memories to the system, and that's some kind of non-local correlation or correlation phenomena. And I mentioned about homogenization, right? If you can think about generically a local derivative forms involving local derivative operators. If you have heterogeneous material, you want to talk about their possible homogeneous limit. There's a known result says the most generic case, the homogeneous limit should have both the local terms and non-local terms. And it's only in some very special cases that you only recover the local ones. Okay. So why we don't see them very often, and this is maybe the other side of the story. The local model turns out, the local reduced model turns out to be another approximation. So once you do this dimension reduction, you may end up with non-locality, but this is way too complicated to handle. So I'm going to try to introduce another approximation to localize this. This can be done by introducing closure approximations, or to say, maybe there's some near equilibrium or scale separation principles allow me to further localize. And if I can do that approximation, get localized, then we feel more comfortable because we get to see what we're used to. Okay? But not all the assumptions are possible in practice. Again, this interplay between local and non-local, I won't have time to go into detail, but I have a few examples like superconductivity. I was talking to Alex about superfluidity. So that was a good example of you have a model start from a local many-body interaction homogeneous structure, and then derive a PCS theory for the gap equation to really explain the nature of why superconductivity will form. And that was a non-local integral equation. And then later on, people realized that you can actually derive the local Ginzburg-Landau model, which is totally phenomenological from the PCS theory. Now, there are other examples, like from Newton's law to Boltzmann, which could be viewed as some non-local equations with closure and so on. And then to Euler and Navier-Stokes, and that goes to local again. So there are many examples in this process of doing model reduction that you probably will end up with something non-local, and then you can try to further localize them in special cases. But generically, it's going to be non-local. Now, another sign where I think if you're working on problems where you might sense there's some kind of singular behavior, like distortion, it was trying to model cracks, fractures, and so on, then that may be a sign to consider non-local models. Because most local models are derived for smooth quality of interest, right? And then you can allow to take derivatives. Now, PD analysts try to make sense of those traditional equations, even when solution is not very nice. You can introduce notion of weak solution and so on. But I would say often the fact that near the solution singularities, there could be loss of underlying physics, and that should create problems for the modeling or for the mathematical analysis. For example, for hyperbolic conservation laws, right, shock and discontinuities, you may have the loss of the entropy condition. So because of that, you may end up with, if you consider weak solution, you may end up with non-unique weak solutions. Right? Now, non-local model on the other hand, will try to retain more physics into the problem. And possibly by replacing the derivative by integral operators, it can operate on quantities which are not very smooth, and yet still make sense. Making sense not only mathematically, but also making it more convenient to do numerical computation. And you have to imagine that computational is always more dangerous to differentiate, but it's always more robust or safer to do integration, to do averages. So this has a lot of trace to this. I mentioned paradigms already, right? But I was using the bound-based model as a particular example, but certainly Schilling had developed a whole machinery to derive this nonlocal mechanics models, basically by replacing Newton's law, which in space when you have the standard derivatives, he replaced that all by a spatial average integrals. And there were beautiful examples. Maybe Kim was referring to some of this a little earlier. We have a projectile hit a target, you get lots of fractional patterns. It would be very hard to do this using a traditional numerical methods for solving PDEs, but this seems to be pretty successful for prey dynamics, and we've done some of this as well. So this is a sign that we will replace the traditional PDEs by this nonlocal paradigms model. You allow the displacement to form discontinuity, and this gives you a more effective or robust prediction of material failure. So that could be one advantage of considering nonlocal models if you want to consider singular or solution processes which are not so regular. Okay. Now let me move to the other side, which is often what we're interested in is perhaps not a lot of details about what the process is, but we're interested in some kind of statistics, right? So the appearance of anomalous statistics can also be a sign where perhaps there's some nonlocality in play, right? So one example, typically for diffusion processes is your mean square distance, right? How the mean square distance travels with time. And if you have an underlying Brownian motion or a Markovian process, so you expect that we're going to go with a linear scaling law. But if in practice, when you collect those data, you see scaling laws which doesn't behave linearly, or maybe there are some other more general stochastic process in play, or there could be memory effect, maybe Markovian. So this so-called anomalous diffusion ranges through subdiffusion with memory effect to superdiffusion, which accounts for processes like Levi-Flies, jump processes, right? So this is another sign. Maybe the equation you want to model could be nonlocal. And let me show you one particular example where we did a recent work with what we call as a nonlocal in time dynamics. So I write down the normal heat equation or the nonlocal diffusion equation on the left-hand side. Then on the right-hand side, there's a so-called fractional subdiffusion, where you replace the time derivative by a fractional in time derivative. So this gives you a time correlation and a time memory effect. Right? And it's known that the fractional in time equations will give you the subdiffusive behavior in comparison with the normal. Okay? But this is the process, right? If you go with a normal diffusion, you'll get the strict linear scaling. If you go with a fractional subdiffusion, then you're going to get a sublinear scale. But there were a lot of recent experiments, so I listed some of them here. They show that for diffusion in a heterogeneous environment, the process can go through different stages. So for example, initially it could be subdiffusive, but as time goes on, it actually starts to be more and more like normal. So eventually it will become a normal diffusion process. If you try to model that, and if you want to use a single model to capture this, then neither normal diffusion nor the fractional one is going to fit the bill, right? Because they can only capture one end of the other. So what we did is we replaced the derivative by a nonlocal derivative operator. So rather than having no memory, which would be the normal diffusion, or having fractional diffusion will be accounting for all the time history starting from time to zero, right? You keep track of all of them. We're going to say, I'm going to allow this to have only a finite range of memory, parameterized by delta. I only loop by in time over a finite range. So if you solve this kind of non-local time dynamics, turns out, with deep simulations, then initially it's going to be more like a self-diffusive behavior for properly choosing kernel functions. But then as time goes on, it's going to behave more and more like a normal one. And intuitively, so not to say mathematically you verify this, but intuitively it's not hard to understand this either. If you only have finite memory, and if you're very young, then when the process gets started, then pretty much you remember everything, right? That's all your time history. But if you have lived thousands of years old, and you can only remember what happened in one day, that's almost like you have no memory. So the effective memory becomes much less dominant. And so this is why, as time goes by, if you only remember a finite amount, then the longer history you have, well, the longer time you run, then the less memory effect you see, and then you're pretty much going to get a normal diffusion in N.
Can I ask a question?
Yes.
In a case like this, how do you choose the omega delta?
That's a good question.
For the real computations, that's where the modeling is. No?
That's right. That's a million-dollar question. So this one is illustrative for illustration only. We're just going to say that if you pick a kernel, then properly you can generate different kind of scaling or statistics, right? But which one actually maps the particular experiments? That would be a data-driven modeling issue, or totally correct. But there's more than to this. So I think so maybe answer to your question is that there probably is more than one equation that's going to fit the single statistic, right? But that's to say, if you really want to model the underlying dynamics, collecting this statistic is not going to be enough. Right? So you may need to collect other type of statistics together to figure out what is really the right model to fit this. And certainly, those are wonderful questions, very interesting questions.
So do you have a family of omega that you can analytically understand the scaling?
Correct. Yeah, so we know for what kind of kernels, what typically analytically we're going to expect, right? And we can pick a few to say, oh, okay, this one looks like it fits the curve of their experimental data better. But that doesn't mean that this is, the only model you can do. Right? All right. So I guess the message is that, by working with this nonlocal model, you can capture this transition from subdiffusion to normal diffusion, and you can see if you use nonlocal models, you can model many more general diffusion processes with various different type of normal statistics. That is my main message. Okay. All right. So let me move to another one. So we talked about perhaps nonlocal model could come generically, and nonlocal models could be convenient to treat singularities. Nonlocal models can provide you a lot more statistics. But there's also another reason that maybe nonlocal model doesn't really, is not meant to replace the original equation as a physical model, but it's just for some mathematical or computational convenience. Right? So here I give you one example. This relates to the method of smooth particle hydrodynamics. This was many years ago by actually astronomy or astrophysicists, and they were trying to study the collision of galaxies or stars to solve hydrodynamic equations, but they want to use measureless particle methods, right? And then they find that it's more difficult to apply derivatives on those distributions directly because you're thinking about those particles as delta functions. But rather, one way they do differentiation is to say, well, if you have a quantity of interest, you want to differentiate that in space, you don't do derivatives right away. Rather, okay, you replace that differential operation by some kind of with a nonlocal smoothing, okay? And over certain length scale, I use delta, but they call delta like a smoothing length. So it's like we replaced a integral operator, replace a differential operator by something nicer as an integral operator. Then for this integral operator, you can try to discretize that using something called quadrature rule. Okay? Then you put those quadrature point and the particle positions, you collect all the sum together, and that allows you to do the computation very conveniently without having to introducing like geometric meshing or other things that could be complicated for complicated geometry. So this method is very popular. Actually, you can find thousands of citations in the literature. But to me, it's surprising that it's my, I heard other people talk that if you're working on SPH, then it's either you like it very much or you totally dislike it. Right? So it's like no middle ground. Well, people like it really find it convenient to do. Right? No meshing. there's not much learning curve. You just apply this two-step machinery. It's easy to implement. But the people who don't like that is they find this problematic, like very sensitive to your particle distributions and other things. So there is a mystery. For example, says that people know how to define smooth particle Hydrodynamic gradient, so how to discretize gradient, how to describe divergence, how to describe Laplacian. But there was advice saying that you should not use the composition of the SPH divergence with SPH gradient to be the SPH Laplacian. And that's a bit of strength because traditionally we take divergence gradient to get local diffusion. Right? So why can't you do that with SPH? And so there are many mysteries like this, which makes the method annoying to some of the users, and then we find it difficult to understand. So I would say that in some sense, we run into issues like this, not on the level of numerical methods. It's actually on the lack of understanding of the nonlocal model. Okay? So you can sort of try to forget about the second step with your quadrature or particle discretization. You can think about this process of replacing derivative by a smooth integral operator. What's going to be the impact of that does for your mathematical model? Okay? Because that might have changed the nature of the equation itself dramatically. And then maybe no matter what you discretize, if the model itself is not well posed, you're bound to generate some issues one way or another. Okay. So we did analysis of this type. Basically, there are two issues. One is there is smoothing scale delta, and then there is also particle spacing h size. So you can talk about what relation between those scales and which scale is smaller, which scale is bigger, and in different situations, do you have to worry about the different type of nonlocal smoothing or the particle discretization? So there's a lot of discussion of that nature. I won't go into detail, but our message is that if you spend time to study what is going to be the nonlocal continuum model, where you replace the derivative by nonlocal differential operator, then maybe it can offer you an idea to generate a better continuum model. Then you discretize that. You could avoid having issues like what was talked about before. So if you have a different SPH divergence or SPH gradient, then you could combine them to get SPH Laplacian in a computationally reasonable or robust way. This is something that is a byproduct of introducing smoothing relaxation as a mathematical tool to understand the existing numerical methods. It's not trying to say this nonlocal model is going to be the equation of motion for fluids or anything. It's purely for the analytical convenience, but it does offer you some insight to say what you should do in computation. Now, let me move to maybe the last example here. Well, actually, so I briefly mentioned this because I think we're living in a world where we see increasingly noticeable long-range interactions. So maybe we should try to keep that in mind. One of the examples we did, there's a lot of other studies connected this to like social dynamics, data learning, and so forth. But one particular example we look at is traffic flow models for very classical one, this so-called LWR models, where you write describe the traffic as a density function of car density and write down as a local conservation model, right? And this is with the assumption that basically your cars are going to be driving with a speed that only depends on the local density. Okay? But if you think about vehicles are now connected through wireless communication or many other things, cell phones and so on, GPS, so you could have information about the density not only locally happening at this particular time and space, you could get a lot more information. So the question is, can you utilize those non-local information to end up with a better driving condition? Right? So one of the better driving conditions is to say everybody drives with uniform speed, so you like to generate uniform flow, even though initially it may not be uniform, and then that way it may be more economical. Okay? So we look at this problem, and there have been related studies in the literature, right, where the velocity field now is written not as a function of a local density, but rather as an integral average of some non-local density. Okay? So you end up with a non-local conservation model. Right? So there were studies about the mathematical property of this equation in terms of well-posedness and consistency with local model and so on. But what we did with student Qiang is to study the stability of this nonlocal traffic model. Right? So we want to know, as time goes on, whether we're going to achieve, for example, a uniform flow. And we know that's not the case for the traditional LWR model. They can form shocks, they can form all kind of periodic patterns in space. Okay. Okay, so I don't have time to go into details, but we'll say if you put the weight function property, so you're going to weight the density information, say for all the cars maybe in front of you, right? If you know the information for the cars ahead of you, and if you weight them properly, then you can stabilize the traffic. But if you don't weight them properly, then you don't form that kind of stabilizing effect. In fact, the conditions we get is completely sensible. We're going to say that you need to utilize the non-local information. It's going to have positive effect, but only if you weight the information closer to you or heavier, right? Which also makes sense because you don't want to make a decision based on cars far ahead of you and not worry about the local density. Okay, so account for non-local density is important, is helpful, but you need to account for them in a proper manner. All right, I see I probably put too much stuff in this lecture. Now, I mentioned about what are the signs for local models, but certainly there are many challenges. So first of all is what type of non-local models should we use? What type of non-local interactions should we use? This is very important and something I really want to study more. And you can think about two ways. One is derived from fundamental physics, coarse graining, but the other one is data driven. Right? So this is a very important thing, Okay? But beyond that, let me just maybe spend a few minutes talk about if you're from a mathematical side, what are the new mathematics that can be interesting for non-local model beyond the ones you know already about PDEs? Right? Can you say something new about the non-local mathematics? And maybe also the numerical methods. I'll try to finish this up more quickly. Some of the stuff can be found in my book that Alex showed you. Okay? We were particularly interested in non-local models of a special type, which is system non-local models, not for scalar equations, but also involving a finite range of non-local interactions. Because this allows you to link with the fractional models, which will be the infinite limit, and also local models, which will be the zero range of interactions, right? Of course, that study was really is driven by applications. Mechanics, paradigm is one, but also HPH for CFD and so on, but also for trying to understand geometry of data, learning and so on. When you work on mechanical models for vector or tensor quantities in system equations, it has much richer structure that you can play, right? Rather than the scalar equations. So that's another advantage. And then there's also, many new mathematical results you can derive. Okay? In terms of non-local observation, I know some students are working on this kind of aspect. Okay? The study of non-local model allows us actually to sharpen some of the classical results that you may have already learned in your lectures or your courses. Right? When you analyze linear PDEs or elliptic equations, you study things like Poincare inequalities or Cohen's inequality, or if you want to understand the well-posedness, you want to understand the trace theorem to define the right type of boundary condition, all that. So we have made some attempt, right, to find what are the non-local versions of them. Right? And they're not the copycats. Oh, this is a local one, I tried to make it non-local. We are just trying to say the non-local model, the non-local version actually is probably more natural than even the original local version. I don't know if we have a couple of slides here. So here's one comparison, right? Typically, we can have on the right-hand side, we can have a local PDE model. I use L0, U0 as an example. Defining a domain, then you have a boundary condition. Right? But now, if you look at the non-local one, because our non-local involve a non-local range of interaction of finite size delta, when we impose boundary condition, we don't impose a local boundary condition anymore. We impose this on a layer of interaction. That's what typically done. But you can do other type of boundary condition as well. This is a very interesting question. And you can find relation between them when the non-local range of interaction goes to 0, then you can recover the right limit. Now, of course, to study this is a bit maybe too easy here. The classical one has some Subdivision inequalities. Maybe you learned from tracing inequalities. You learned from function analysis or Subdivision spaces. Right? We actually have a non-local analog of the same version. It involves norms defined in the non-local spaces. Right? But they're making much more sense in this in a way that we're just trying to capture the interactions between functions on the different scales, right? And we're going to be able to say this actually works for non-local space, but also when delta goes to 0, it actually recovers your original local version. Right? So it is indeed not only a non-local analog, but it's a generalization. And there are many kinds like that. This is another example where we want to study a non-local model that actually changes seamlessly to a local one. Right? Imagine you have a problem that you may have a larger computational domain, and you only wanted to use non-local model in a smaller domain. And so what we can do is we're going to set up a non-local range of interaction which is non-zero inside a smaller domain, but we'll let that non-local range of interaction go to 0 outside this smaller domain. So you better be able to couple this non-local model in the interior with some PD models in the exterior, and this will need to allow you to match the traces together. We actually also end up with new trace theorems for this type of non-local models involving a vanishing local horizon. So when the horizon goes to 0, when the particle goes to the boundary, and we'll be able to say this type of non-local functions or non-local function spaces will allow you to have the right local traces. And this is, again, a sharper and more natural analog of the local one. So with all those mathematical machinery, I would say, maybe in the last 10 years, we're able to establish some rigorous foundations for non-local models like Hydrodynamics, and also resolve some of the earlier misunderstandings surrounding those non-local models. And finally, maybe I'll just say, this mathematical analysis also allows us to develop maybe more robust numerical simulations for those non-local models. And one of the very important aspects of this can be summarized in this slide over here. For non-local model, we consider with a finite range of interaction. Once you discretize that, you actually have two length scales. You have this non-local range of interaction, but you also have a discretization parameter h. Right? Now, in practice, those two parameters could all be varied. For example, in this non-local local couple model, we could have the non-local range of interaction be positive and going to 0 and stays local, right? So there could be a range of delta ranges, and then couple that with crystallization. What's important is that we want to make sure that the models are consistent at the continuum level, but also it's going to be consistent at the discrete level. Okay? So one way you can think about is you may have a non-local continuum model with a solution U delta, and when delta goes to 0, it goes to a continuum local PD solution. Right? But you can discretize this continuum model using a step size, using a mesh size of particle spacing h, get a discretized non-local solution U delta h. As you refine your spacing, you could resolve the continuum model. But the question is, if I make this non-local range of action goes to 0 simultaneously as the mesh spacing or the particle spacing mesh size, will I be able to recover a solution of the PD model? It turns out that's not always the case. For example, in the early schemes proposed by Qiang and others, they were using very simple-minded numerical quadratures to do the visualization. And it turns out that for those schemes, you're not going to get consistent local limit. And that can be a problem because it will be very hard to benchmark the simulation you get from Hydrodynamics with the simulation you get from, say, Abacus, or solve PDs and so on, right? But if you are doing it better with this kind of what we call asymptotically compatible schemes, then you can assure that you always end up with the right limit. It doesn't matter what's the relation between the non-local range of interaction and the matched spacing. All right, so with that, I should really conclude, and hopefully I well, this is supposed to say a little bit more, but I'll skip this. To say that, well, local models actually are special, right? And they were derived originally for smooth quantitative interest, but nonlocal models certainly are much more generic, and it can be more suitable, effective for anomalies or singularities. There's certainly a call for nonlocal models nowadays, but it's still at a very nascent stage. There are a lot of new mathematics being developed, numerical schemes, but certainly a lot of more questions and challenges. And hopefully this would interest some of you sitting here and to study more, and I'll be happy to talk